Hi, I'm Shale, and I'm here with Gerardo and Navneet to talk about lab number 5. Pendulum motion involves potential energy being converted into kinetic motion. How long the pendulum takes to swing back and forth depends on length and the effect of gravity. The longer the string is the longer the period, or the time it takes to swing back and forth once. We started by counting the time it takes for the first 3 oscillations to occur. Then, using Hooke's law, we found the relationship between angle and distance traveled over time of this pendular motion. We hypothesized that the angle will not affect the periods or the oscillations of the mass during the same amount of time. We think this because the angle of the pivot should not matter. The only factors that would affect the period would be the length of the string and the mass of the object. By testing and timing these first 3 oscillations, we can reduce certain factors such as air resistance and friction and find a more accurate data set.
Okay, so I'll be going over the specific details about our data collection. Now, in order to attain the data necessary to complete this lab, we first had to start off by setting up the pendulum experiment. And this involved us using a string, a weighted sphere, a protractor to measure our desired angles, and a stopwatch to measure the time that it took to reach 3 oscillations. We started off by cutting the string to a length of 35 centimeters and attached both ends of the string to the weighted sphere and the pendulum stand. From here, we proceeded to test whether the pendulum actually worked by pulling back the sphere at a certain angle and releasing it to see whether or not it oscillated and how well it did oscillate. Now, to account for error, rather than only measuring the time that it took for the pendulum to oscillate one time, we decided to measure the time that it took for the pendulum to oscillate 3 times, as it would have been pretty hard for us to measure the exact time of one oscillation. Now, here's our first data table where the constants here were the length of the string and the mass of the sphere, as we are looking to see how well or how the angle used affects the period of a pendulum. Now, the varying component, as I just mentioned, is the angle. So for this first trial, we decided to use an angle of 85 degrees, and the time for each of the 3 trials varied by nearly 1/10 of a second at 0.09 seconds. And the actual average of the 3 trials to reach 3 oscillations was 3.38 seconds, and we calculated our percent error to be 5.056%. Now, here's our second data table where we use an 80-degree angle this time, and once again, our string length remained the same and our mass of our sphere remained the same, as we are only looking to find how the angle affects the oscillation and the period of a pendulum. Now, this time, the average for the 3 oscillations at the 80-degree angle was 3.4 seconds, which is only 0.02 seconds longer than the average that was found at the 85-degree angle. And once again, we calculated our percent error to be 4.494% here. Now, here's our third and final data table where we used an angle of 70 degrees to measure the time that it took to reach 3 oscillations. Once again, the remaining variables stayed the same of string length and the mass of the sphere, as we are only looking to see how the angle affects the period and the oscillation within the pendulum. Now, this time around with the 70-degree angle, we found an average for the 3 oscillations to be 3.44 seconds, and our percent error that was calculated at 70 degrees was 3.37%. Now, this graph right here is a representation of the average time that it took for the 3 trials to reach 3 oscillations and the angles that they were used at. So here we can see the angles on the left and the time on the right, or sorry, the time on the x-axis. And one can see here that the relationship is quite linear between the 3 angles. So what this does is allow us to come to a little bit more of a conclusion on our hypothesis that was that the angle of a pendulum does not actually affect the period that is produced and the oscillations that occur from it. And I'll go ahead and let Navneet get into more of these details in the discussion. Thank you.
Hi, my name is Navneet Kaur, and I will be going over the discussions and the conclusions. So for our lab, we basically had a frictionless pivot, which we tied a string off to mass, and we set a desired angle that we wanted to test this theory or hypothesis on. And we use the equation time is equal to 2 pi square root of length times gravity. For our experiment, our angles that we tested were 85 degrees, 80 degrees, and 75 degrees. The mass remained constant. It was a mass of 25.7 grams. The length of the string was 35 centimeters. This also remained constant. And gravity also doesn't change here on Earth. So it stayed 9.8 meters per second square. Our percent error was a little high, and we did feel like we may have ran into some errors. One of them being human error. The time it took for us from letting go of the pendulum and starting the timer and then stopping it again had some delays. Even if we even had a trial where one person was holding or letting go of the string and the other person was doing the timer, that actually had an even higher percent error because of the time it took from one person to convey the message to the other person and then pressing the timer. So that definitely there was room for human errors. Then we did notice during our trials, there was air conditioning that turned on, and we feel like maybe that could have caused some resistance. It would be very small, but it does take into effect. And then wobble was because our pendulum stand had a slight wobble to it. So we're not sure if it created some opposing forces during the experiment. For our conclusion, even though the percent error was high, our results were fairly consistent with our hypothesis, as Shell described earlier. As our angle decreased, our percent error also decreased. This further justified the fact that it may have been because of human error, where it was at 85-degree angle. We felt like there could have been more air resistance because of the mass had more air to travel through. And we did feel like that air resistance could also contribute to the higher percent error with the increase of angle.